Turfgrass lawns are common in urban landscapes. According to high-resolution satellite images, the lawns cover nearly half of the total urban area in the United States. Irrigation of urban lawns may consume up to 50% of municipal water. But how much water do the lawns actually use? In fact, it's not easy to measure. Most of the water that plants use is transpired through leaf pores. Water may also evaporate from wet leaves and the soil surface. The total water loss is called evapotranspiration. There is no way to measure evapotranspiration directly. Current state-of-the-art methods are based on precise measurements of rapid atmospheric changes, data from satellites in outer space, and numeric simulations. While these methods provide the best large-scale estimates of evapotranspiration, at the current state they are not able to capture the footprint of small urban lawns embedded into a patchwork of streets and buildings. As the lawn is losing water to evapotranspiration, it becomes lighter. Placing a lawn on a scale and measuring its weight loss would be a good way to measure evapotranspiration. However, installation of weighing lysimeters in the soils under city lawns is not very practical. We are going to use rapid changes of humidity right above the grass surface to deduce evapotranspiration from urban lawns. But when we simply place a sensor on or above grass, it does not record any changes of humidity. This is because the air adjacent to the grass is constantly mixing with the surrounding air. We can temporarily stop this mixing by placing a small chamber on top of the grass. If we leave it there for a while, it will highly alter the conditions near the grass surface. Temperature within the chamber will grow, and evapotranspiration will slow down as water vapor builds up, fogging the chamber. But when we look at the sensor readings during the first 20 seconds of chamber placing, we see a linear increase of humidity, which is directly related to evapotranspiration from the surface below. We use data loggers with built-in sensors and program them to measure humidity and temperature every 2 seconds. Placing a data logger on top of the grass or attaching it to a chamber wall provides similar data. We attach the data logger to the chamber. We add an identical data logger in case of a battery failure in one of them. Before measurements, the chamber should stay outside in a shady place for 20 to 30 minutes. This will allow the sensors to adjust to ambient conditions. To make a measurement, the chamber needs to be placed on a lawn and tightly pressed to the surface for about 40 seconds. Between measurements, the chamber should be ventilated with ambient air for at least 1 minute. To record diurnal changes of evapotranspiration, we make a series of 6 measurements at each lawn and repeat them 5 to 6 times per day. This is a simple procedure and could be done by a high school student or even a kindergartner. Well, maybe not. The environment inside the chamber may be quite different from outside conditions. There is no reason simply to trust a chamber measurement, even if it's very fast. Chambers suppress incoming radiation, alter air pressure, block near-surface winds, increase air and surface temperature, and change the concentration of water vapor. There is no 5-second rule. Therefore, calibration is necessary to assure the reliability of these measurements. We carefully calibrated the method by weighing lawn pieces on a precise scale to capture weight losses caused by evapotranspiration. We sealed the lawn pieces with plastic wrap to avoid leakage and ensure that the only path for the water to escape was evapotranspiration. We made chamber measurements and corresponding weighing under different environmental conditions. We traveled to the Anza-Borrega Desert. The air temperature was 100 degrees and the humidity was 10%. Our goal was to expand the calibration to the hot and dry extreme. These efforts produced a robust straight line, from which we developed equations to calculate evapotranspiration from chamber measurements. These measurements help improve our knowledge about evapotranspiration from urban lawns, which is necessary for understanding urban water budgets and developing sustainable landscaping solutions.